for B, the quaternion, over Q, I want to show that first of all, the ramified place is finite. And the cardinality is even. So let's stare at the table for a bit. So we have this classification of quaternions over the local field. At least when P is all prime. And if you look at the upper left 2×2, it says that, I mean, basically, if I want to play the following. So if I guess P odd and A and B are both p-adic units, and they don't, their value is 0. They don't have P in them, basically. Then I want to say that their Hilbert symbol is 1 in the table. That's what happens on the left, upper left 2×2. So that, or put another way, if you look at sort of the quaternion with this property AB, that's just the matrix. As I work into the matrix, you can always show that. So then, what does this imply? This implies that now, if I take two rational numbers, A, B, I want to say that for most of the prime P, it doesn't divide the numerator denominator of A and B. So for most of the prime, it's for all, but finitely many prime P. This AB rational number can be viewed as a p-adic number, and they are in ZP cross. Because I mean, as a rational number has numerator and denominator, they can only have finite many prime factors. Away from these finite many prime factors, they're invertible in the corresponding ZP. So what it says is that when these two together, it means that this Hilbert symbol is 1 for all, but finite many. So that checks the finiteness. I need to show even. So that's, I think, the most, the deepest part of this. Just use the following. It's called Hilbert platform or Hilbert reciprocity. So for if I have two rational numbers, I want to know the set of places of the corresponding quaternion where they ramify, where they don't isomorph the matrix. So this thing says, this product formula says that if you take the product for all places of Q of the Hilbert symbol at the corresponding place, the product. I mean, first of all, this is, each one of this is plus minus 1, so the product will be, again, a sign. Affirmative is always sort of 1. Let me make a really quick remark that suppose that it's going to be an infinite product, which I take the product of all the places, infinite many primes. But we know that A, B, P in the Hilbert symbol is 1 for all but finite many P. So if it's 1, you don't have to really take it. You don't have to really multiply it. So really, this is actually a finite product. And what this implies is that you take product finite many plus minus 1s. That means the number of minus 1s is really even. That's how you get 1. And what's the number of minus 1s? This is the same as the number of the ramified places, as we defined earlier. Yes?
Can you remind me the Hilbert symbol for the infinite place?
Yes. So we'll use that later. So I'll write it down here. So how about this? So 2 plus it. Okay. So 1 over 1 if A is positive or B is positive. Negative 1 only if both are negative. I want to write plus 1, for example. Yes? At 2 we have a formula, right? It's a little bit more complicated. Yes. We also know how to do it. P equals 2 always takes extra effort. I won't be able to present the yes, there's a formula. And I put it, oh, I didn't do it. You can read this book by Sarah, Courses in Arithmetic. Everything I lecture is how you probably find it there, or some shadow of it there. And there he explained somehow. There's a formula. He said, sure, there's a formula. So all these things we can find, but the problem is that for arbitrary A and B, we want to prove this global function. Proof goes as follows. First of all, we note that the left-hand side is by multiplication. So if, say I want to prove this formula for because each factor is bimultiplicative. If you want to prove this for AB, and suppose B factors is B1 and B2, it's suffice to show this for AB1 and AB2. Right, because it's multiplicative. And if you show it for each factor, it's local Hilbert symbol multiplied to 1, and then for AB, the local Hilbert symbols will multiply to 1. So now, we immediately reduce this to show this for where AB are in the set of -1, because every rational number, non-zero rational number is a product of -1, 2 is special, and some odd prime. I mean, odd primes. You just need to really kind of exhaust all these cases and really just exhaust all. The main reason you have to kind of make this trouble is because it's 2. So let me do a easy. So the first case, when A equals 1, A equals B equals -1. Okay. So because of this, for any odd prime number, if A and B are not divided by P, their corresponding Hilbert symbol is 1. So in this case, if I do Hilbert symbol as P or P odd, it's going to be 1. P odd. It suffices to check the other 2. So the question is, what is this, and what is AB2? Right. So infinity is -1. And I guess if it's to be true, this has to be also -1. Of course, I didn't get time to actually do the computation, and if you go down the computation, you can actually check the second -1. So theorem checks in this case. Maybe I'll give a kind of a working formula for Hilbert symbol at 2, so we can use later. Take it as that. And if A and B in actually Z2 cross, neither A or B are divided by 2, then the Hilbert symbol is equal to, it's not it's not 1. So it's slightly, you see, it's slightly different from the case of the off prime. So this is depending on what it looks like modulo 4. So the best way is to write this like this. So if they're both common to 1 mod, if one of them is common to 1 mod 4, the hero symbol is 1. If both of them are common to 3, the hero symbol is negative 1. So that's the case when both of them are common to 3 modulo 4. So that's hero symbol is negative 1. And of course, you have to check lots of places. I'm just gonna skip this, and as an exercise, you should kind of try to check all these. So from case 2 to 6, you're gonna check the following list. For example, -1, 2 versus 2, or -1 versus a prime. It's an odd prime, and you have to check, I don't know, 2 and 2, and 2 and the odd prime. And there are also cases where both of them are the same odd prime. For those 5 cases, enumeration. Check one out. I wish there's a better way. But I mean, you see, these are somehow relatively easy checks. This last case I want to emphasize, where A and B are prime numbers, but they're different odd prime numbers. P and L. Odd, P not equal to L, but they're both odd primes. And let's check this last case. So what do I know in this case? I'm going to plot it over all the places, right? If the place is not, it's a third prime, a third odd prime, different from P and L, the Hilbert symbol is 1. Right, so Q odd prime, and Q not equal to P and L. Okay, so that you can kind of ignore. Okay. And infinity is also 1. So what else? I have to check 3 more things so that I can compute the product. I have to check, compute this at P, Hilbert symbol at L, and 2 is something you always have to compute, unfortunately. Okay. So basically, the product formula tells you to take the product of this, an infinite place, and all these 3. And you want to show the product is 1. Very quiet. We should be quiet. We are talking. Let's take a quick look at the formula here. So this last formula over here. So this formula for this Hilbert symbol. So we're in a case, for example, when alpha is P. So ignore this. So A is P. So alpha equals 1, and U is 1. And B is a unit. Right? For example, PL and P. So A will be P and B will be L. L is prime to P. So we're in the case that, so A is just P and B is, there's no beta. Beta is 0 and alpha is 1. Okay? So if beta was 0, it's something 0's power that's 1. So this term can be completely killed. And if beta was 0, then this term is also killed. Right? So just left with the correct symbol V over P. So that's just L over P to the first power. Okay? If you didn't see that, sorry. Sorry, it's questions. Same here. If you do it at L, you get quadratic symbol P over L. At 2 is always weird. It's that whatever. Yeah, weird. Folsom. So what does Hilbert product formula says? It says that if you take the product of the Hilbert symbol over all the places, that equals 1. In this case, somehow if you think of this as a majority case, because these cases only depend on one prime, and this is a place where you have involve 2 pairs of primes, pair of primes, so somehow the majority case. This is equivalent to the following statement that L I should multiply it, but then because it's plus minus 1, I can move it either side. This is a Gauss quadratic reciprocity. So, and in fact, I think the Hilbert product formula we stated earlier is equivalent to a Gauss quadratic reciprocity in this equality. Asking whether L is a quadratic residual modulo P and whether P is quadratic residual modulo L. I guess if, as long as one of P or L is common to 1 modulo 4, then the L is a square mod P, and then P is square mod L. Okay. How do we prove the second? How do we prove the Gauss quadratic reciprocity? Honestly, I don't remember. There's a proof here. Come on, zoom in. This is the original proof of Gauss. Okay, good. Ask Alvaro. Ask Keith. I've got one. So we can see that done, because there was a proof. There's a proof here. How much time do I have? No time?
Negative 4 minutes.
I'll end here then. Well, I only proved 1/3 of the theorem. I think I'm still far from, but it's 1/3 of what Gauss is like.